In this lecture, we're going to look at some fairly standard calculus questions. Most of these, for example, finding the equation of a tangent line, should be familiar from back in Calc 1. The difference here is that we're going to be answering them using our new parametric equations instead of the old rectangular ones. Now, this is a relatively straightforward example. We've looked at these specific equations before, and we've seen that their graph is a unit circle. So based on this, we already know where the tangents are, but there's still value in doing these calculations. This is a common mathematical technique when developing or learning a new idea. Since we know what the results should be, we can use this to check the accuracy of both our method and our calculations. So to find the tangent lines, we're going to use the standard method from first semester calculus. We need to find the function's critical values, that is, the points where the derivative is either 0 and undefined, and then confirm that the sign of the derivative changes as it passes through those 2 points. So to find dy dx, we're going to need to use our new formula. And we see here dx d theta is minus sine theta, and dy d theta is cosine theta. So this makes dy dx over here negative cosine theta divided by sine theta, or just negative cotangent theta. So now we can answer our question. The cotangent is equal to 0 when theta equals pi over 2, which is down here. And it's undefined when theta equals 0 or pi. And you can easily check that the derivative does change sign as it goes through all 4 of these points, so they do in fact represent the location of tangents. Now the 2 points where the derivative is 0 give us the horizontal tangents, and the 2 points where it's undefined give us the 2 vertical tangents. All right, so the equations here are the same as in the previous slide. So we know that dx d theta is minus sine theta, and we know that dy dx is minus cotangent theta. Now, the derivative of negative cotangent theta is minus cosecant square theta, and dx d theta is still minus sine theta. Now, since 1 over sine theta is cosecant theta, this simplifies to just minus cosecant cubed theta. All right, so finding the formula here is a straightforward application of our formula. dx dt is 2t, and dy dt is 2t. So that makes our derivative equal to 1. Okay, except, remember that our original formula here had a restriction, except where dx dt equals 0. So that means our formula actually doesn't apply when t equals 0, or it does apply when t is not equal to 0. And to see what's going on here, it helps to go back to the graph here that we looked at in an earlier lecture. The graph is a ray starting at the origin, and just like a line, the rate of change of a ray is constant, which is what we see from the result of our calculations. Also, you can see why we have to include the exclusion that t can't equal 0. When t equals 0, the graph is here at the origin, and that's where the graph comes to a point. And the derivative is never defined at points like this where the graph makes a sharp turn. So this is the end of kind of our basic calculus examples. We've seen how to use the formula for dy dx for parametric equations. We've also seen how to calculate the second derivative and kind of a special case where that special exclusion came into play. So in the next slide, the next lecture in the series, we're going to look at some of the more complicated, more detailed applications of our new derivative of a parametric equation formula.